Think about the most powerful computer you have ever seen. Underneath those flashing lights and sleek fans is a desperate battle against physics. Every single calculation generates a tiny burst of heat, and right now we are running out of places to put it. For over a century, copper has been our best defense, the undisputed king of moving energy. But as our chips get smaller and our AI models get hungrier, copper is starting to fail us. It simply cannot move heat fast enough to keep up with modern silicon. But in February 2026, researchers at UCLA announced a discovery that changes the game entirely. They found a way to create a rare, metastable material called theta-phase tantalum nitride, and the engineering behind it is absolutely brilliant. To understand why this matters, we have to look at the numbers. Thermal conductivity is measured in watts per meter Kelvin. Standard copper sits at about 400. It is reliable, it is familiar, but it is effectively a two-lane road in a world that needs a superhighway. This new material, theta-phase tantalum nitride, hits a staggering 1100 watts per meter Kelvin. That is nearly 3 times the performance of the best copper we have. It is a leap in performance that we usually only see once in a generation. Imagine trying to empty a swimming pool with a garden hose versus a fire hose. That is the difference we are talking about here. This discovery does not just make things better, it makes entirely new types of hardware possible. The problem with heat is that it is not just an inconvenience, it is a hard limit on performance. When a chip gets too hot, it has to slow down to prevent itself from melting. This is called thermal throttling, and it is the reason your phone gets sluggish when it's working hard. Engineers have tried everything to fix this. We use massive fans, liquid cooling loops, and even exotic phase change materials. But these are all just band-aids. They do not solve the fundamental problem, how fast the heat can actually leave the source. That is where the UCLA team stepped in. They realized that by manipulating the atomic structure of tantalum nitride, they could create a material that moves heat almost as fast as diamond, but with the durability of a metal. Now, you might be wondering why we have not used this before. The secret lies in the theta phase. Tantalum nitride usually exists in other forms that are much less efficient. The theta phase is what we call metastable, meaning it is incredibly hard to create and keep in that specific shape. It is like trying to balance a pencil on its tip. If you get it just right, it is perfect, but the slightest nudge will make it fall. The UCLA breakthrough was finding the exact recipe of pressure and temperature to lock those atoms into that high-performance pencil-tip state. This is not just a lab curiosity anymore. Because they have figured out the synthesis, we are looking at a material that can be integrated into the next generation of high-power electronics, and the implications for our daily lives are massive. The real magic of theta-phase tantalum nitride is that it solves the biggest bottleneck in modern engineering. From the chargers in your wall to the massive inverters in electric vehicles, everything is held back by heat. If we can move heat 3 times faster, we can change the world. In this video, we are going to dive deep into the atomic mechanics of how this works, see how it will shrink our hardware by 50%, and look at the economic challenges of bringing a rare mineral like tantalum to the masses. The engineering here is absolutely brilliant, and it all starts at the scale of individual atoms. Let's look at how heat actually moves through a solid and why this new material is so much better at it. The most immediate impact of this material will be in the world of electric vehicles. Right now, the inverter, the brain that converts battery power into motor movement, is one of the biggest and heaviest components in the car. Most of that size isn't electronics. It is the massive copper heat sinks required to keep the power transistors from burning out. By replacing that copper with theta-phase tantalum nitride, we can move the same amount of heat with a fraction of the material. This means lighter cars, more room for batteries, and longer range. It is a virtuous cycle of engineering, where a better material leads to a better overall system. This is how we get to the next generation of EVs. Then there is the AI revolution. Modern AI accelerators like those from NVIDIA are essentially giant space eaters that happen to do math. They are limited not by how fast the silicon can switch, but by how fast we can pull heat away from the core. With TAN, we can pack chips closer together. We can eliminate the bulky liquid cooling loops that make modern data centers so expensive and complex. We are looking at a 50% reduction in the size of AI server racks. Imagine a data center that is half the size but has twice the power. That is the promise of 1100 watts per meter K. It changes the economics of the entire cloud computing industry industry, making AI faster and more accessible for everyone.